So, good morning, everyone. Welcome to today's session. We will be covering principal component analysis today and about how we can deal with it and what is the requirement for principal component analysis and why we do that in predictive modeling or just an introduction. So, if any one of you know about PCA, how it works and why is it required, so anyone can give an introduction or maybe about your understanding that how much you know about PCA.
Yeah, Ankit.
Yeah. Yes, Shashi, please tell me.
So according to my view,
Mm-hmm.
yeah, suppose that in one model,
Mm-hmm.
I have about 200 variable,
Mm-hmm.
but all 200 variable are not more significant.
Mm-hmm.
So, so we are finding the best method
Mm-hmm.
to only the significant variable.
Mm-hmm.
So that time we are using the principal component method. In the principal component method, there we are using two principal one and principal two.
Mm-hmm.
Yeah, according to the principle, we use the eigenvalue and eigenvector and also reduce the sum of the axes. According to that, we can choose the different type of variable.
Mm-hmm. Okay.
Something like that.
Yeah, yeah. So a bit closer. So I will give you a context to understand that how principal component mainly works. So I hope all of you must have done some coordinate geometry in your class 11 and 12 or even three-dimensional geometry and vectors. So you will be having some understanding of vector. So let's say, let me put it in this way. So I have my coordinate. I have x equal to 2, then uh, y equal to 3, and then my z equal to 5. Okay. So this is my x, this is my y, and this is my z. So in a way, these are three different variables for me. But what I have done is I have put them into a single vector. Let's say my vector is v, and my vector v is shown like this. So three different values, but they are put into a single value, that is vector value. So this is what principal component mainly works with. Now if I want to show in my vector in a single line, so what I can do is vector v that will be equal to 2 I cap plus 3 j cap. Let me not do it here. I have a R script, so why I'm doing here. So let me explain it here. So suppose we have v equal to that coordinate wise 2 comma 3 comma 5, and then I have in vector form I can write it like this: 2i uh, 2i plus 3j plus 5k. So hope it makes sense. Here I had three different variables and now I am writing it into a single variable, that is v. So this is a similar type of transformation that we do here in principal component analysis, that all the type of variables that I have, they are merged into a single variable. Not single, but most of the I should say the variability of all the uh, variables are captured into a single. So that is how principal component analysis works. So this is just an analogy to to explain you. So let us get into the theory and try to understand how it works. So mainly when we are dealing with data mining and So problem is not that we have a less of data. If you have a proper repository of data, then actually the problem would be too much of data, and you're not sure about which data to pick and which to lose or which to omit out. So their scarcity of data is not a problem, but actually abundance of data is a problem. So in that situation, what can happen is uh, you find that most of the variables are good, and you lose all your patience. You don't know which one to pick and which one to lose or to omit out. And actually there are 200 variables, and it will be a time consuming process to work with all the data or all the variables, and then to decide which one to take and which one to omit. So it might happen that you might lose out of patience, and you might take all the variables and run a model. So that is where the challenge come, and in this challenge, principal component analysis comes into picture, which helps us. So in simple word, principal component analysis is a method of extracting important variables in the form of components from a large set of variables available in dataset. So it extracts low-dimensional set of features from high-dimensional dataset with the motive to capture as much information as possible. With few variables, visualize becomes much more meaningful. So if you all remember, we had this problem in clustering. What happened is when we made a cluster and when we tried to make a visualization of that, making that visualization on the basis of two variable was not a good representation. The clusters were getting merged up, so a different cluster was getting merged up with a different cluster, and two-dimensional view was not quite appropriate, I would say, to make that visualization. So there what we did is we made a principal component analysis of all the variables that we have, so that the first two variables can explain the maximum variability of all the variables. So what typically happens is my first two variable will try to explain around, uh, let's say it depends upon the data, but as usual, if you have a good data set, then it can explain up to 80% of the variability. Only first two variables can. So what happens is first principal component will give the maximum variability, explain the maximum variability of all the variables. Second will be a bit low, third will be a bit low, and so on. It will go down. So this is what will happen. So here we have an example to illustrate and understand. So let us say we have a data set of this many number of rows, 300 number of rows and 50 columns. So these are my observation and these are my variables. N represent the observation and P represent the predictor variables. Since we have large P, so here this is PC2 or what we call NC2, where out of n uh, points, if we have to choose two at a time, then this is the formula. So we can have so many number of scatter plot, and that number would be quite high. So how to deal with it? So here principal component analysis comes into picture, and what is a good thing about that, this all the variability of 50 variables can be explained with the first n variables only, and first two variables will have the maximum impact. So let us see. So here I have a generalized kind of formula for all of them. So as I explained for the vector in the very beginning, this is somewhat like that. So here I have my p variables. This is my variable 1, this is my variable 2, 3, and so on till p variables. And here I have a eigenvector uh, multiplied to it. So there is a loading component or a loading factor here for the first variable. So for second, third. So 1 means for first one and the first component. So for second one and first component. third variable, and first component. So like this. So similarly, if we were doing it for second component, it would have been like 1, 2, 2, 2, and so on. And so one question here. So if I p number of variables, how many components will be made? How many z's will be made? Correct. Absolutely correct. So if I have uh, p variables here, number of components will be p as well. But only thing is that my first variable will explain the maximum significance of all the variable, uh, and with each preceding uh, variables or component, my significance will reduce. And also one thing here that I want to mention, and which is quite important when you are working with this. So here what happens is we have to scale our data set and put them under the same scale. So scaling is required. So anyone can, if you can try and explain me why scaling is required in principal component analysis. So here when I'm making this equation for z, all of them must be in the same scale. Yeah, yeah. So what could happen is, see, I have a data set where one of my variable is about weight of the item, another one is price of the item, another one it could be date or time of the item, or the manufacturing date. So uh, it will be appropriate to put them under the same scale so that I can treat all of them in a similar way. And there will be a difference in unit, and I want to avoid that while making my prediction. For that reason, I put them under the same scale and make a component of it. And once I've done the analysis, uh, in few situations, what happen is I have to again transform my z back to my variables that I have. So these are also this is also a situation. We'll get to it, or we'll understand with our case studies. Yes, correct. So that will also be a situation like if one of my variable is the temperature and another one is distance. So comparing two of them or putting them under the same component and giving them a multiplication factor won't be appropriate. So that is the reason that we make a scaling first and then we work with it. So here, as you can see, x1, x2, and so on are my normalized predictors. Normalized predictors have mean 0 and standard deviation 1, which is my z-score or z-scale normalization. So let us now take a case study and try to understand. So here I have a simple data set of protein. So last time, if you remember, we have worked with the protein data set. So let me load this and start working with this. So this is quite familiar data set that we worked earlier. Okay, yes, Santosh, please tell me. Okay, so factor analysis is also a part I will be covering in the next topic. So I know this is a good question. Both are actually considered in dimensionality reduction. So both work the same, but there is a bit of difference in it. I want to uh, add this, but factor analysis is a part of different subject. So I will cover that in a next topic. But this is a very valid question that both work in a similar way. The main purpose is to reduce the dimensionality. How it is, I will get to it in subsequent classes. Okay. So coming back to the data set that we have for food. So you all must be familiar with this. So this was the data set that we worked in previous class on clustering. So here we had of sources of protein for a individual, and what was the gram of that protein intake for that individual in that country from different sources. So here I had red meat, white meat, egg, milk, fish, cereal, starch, nuts, and fresh vegetables. So let us try to understand. So here I have all the variables. So now let me do one thing. Let me try to make a correlation between all the variables that I have, ignoring the country because country is a character variable and it won't make sense to make a correlation between country. So omitting country and considering all other variables, let me do that. So here I have -1 that will omit country and consider other variables. So here somewhat I have the correlation matrix. So red meat with red meat will always be 1, but red meat with other if I see. So white meat is not so much. Egg is quite high, milk is quite high. Then cereal is negative. So it seems like the person who takes red meat is low on cereals and nuts. So this is a more or less an understanding of what is the relation between all of the variables. So let us now try to make a principal component and let us try to understand that how we can put them all together in few variables. So here I'm doing the same thing. I'm omitting country and taking all other variables and scale is equal to true. So like I said, scale equal to 2 will make it a normal. Uh, Normalize all other variables. So and that will put them under the same scale. So here I have principal component of all my variables. So principal component 1 will hold the maximum value and these are the eigenvalue that we have seen, that loading factor for 1, 2 and so on and so forth. And for 9 variables, we have 9 principal components. So here I have names of few of the. So let me explain that what it means. So here if I make some, um, so this is my standard deviation. This is my rotation factor or the loading component that we have seen. This is my center and scale. So center will be, that is if I'm considering my main equal to 0, sorry, uh, yeah, main equal to 0 and scaling, that means my normalization is done or not. So here I have a detailed explanation of all of them. So standard deviation is the deviation of principal component, that is square root of the eigenvalues, covariance or correlation matrix, though calculation is actually done in singular values. So mainly the standard deviation and how much it varies. Rotation is a important thing to understand because that will be mainly my loading components or the eigenvalue that I have shown you. So that value is actually the rotation factor here. X is so X I have not used so much, and I don't think it is used. So you can ignore this part. So apart from that, these are the main things that are required, and center and scaling. Center and scaling is mainly for normalization purpose. So let us make a plot and try to understand here. So here I have, so if you remember, there was a eigenvalue or say, so here what happens is this actually shows that in the that vector notation, how much close is one variable to the other. If I try to make a plot, so here if I consider this is my 0, 0 point, and here I have some degree or angle with my 0 and 0. So this will be a, uh positive. So it is mainly a cosine of this. So this will be a positive sign. And then this fresh vegetables and fish. So this fresh vegetables will again be positive. So anything above this will have a positive sign, and anything below this will have a negative sign. So I know I'm confusing a bit, but let me run the code and explain. So here if you see, here nuts are 14 around this, and fresh vegetables, if you see fresh vegetables and fish, the magnitude of both of them are quite similar. So no, not the relation, but mainly the rotation factor it provides. And if I go with starch, then starch is this value. Yeah, yeah, correct. And then below this, I have all of them as negative. So if I change it to principal P1, so here if I see my fish will be negative because this is the zero line for principal component 1, 0, 1, 2, 3, 4, and fish is on the negative side. So here I have fish in negative. Starch will be like a negative sign. So in this line, this side is all my negative and this are all my positive. Again, if I do it for PC2, which I did earlier, so anything above this is positive, starch, fish, fresh vegetables, and nuts, and anything below this is negative. So on the basis of rotation of these two, I've made this plot of uh, this what I'm getting currently. So So here mainly I have the variance that is explained by my components. So my first component makes maximum variance or explain the maximum variance. Second to some extent, third goes down, and with each and every value is it keeps coming down. So first few variables are my key. They will explain the maximum variance, and I don't need to consider anything after that. Or mainly I can omit most of them. So this is the main feature of principal component. So the first component that has the maximum variability that will be or which can represent the maximum variability will be put into in first in the order. Then comes the second, third, and so on. So now if I make a cumulative plot and try to explain. So here, see, so proportion of variance explained. So here I have for my first, I would say my first component, then second component, third, fourth, and fifth. So till fourth and fifth, I think most of the variants or even till here, most of them are covered. After this, there is very little explanation provided by these components. So these are not in much use. First four I can take them and I can use them. So using this graph, you can understand and comprehend that which are all the components that will be required to mainly show the explanation. And usually when we do any principal component chart, like we have seen in the previous classes for clustering as well, I have considered principal component 1 and 2 only for the plot. So even if you go to the last class video for clustering and you see for countries or for the same data set that we were working on protein data set, you can see that only I have used principal component 1 and 2. And it gives a fair bit of idea that how most of the data points are placed. So here I have principal component 1 and 2 and 3 and 4. And here I have plotted all my countries name. So how much close one country is from another based on principal component 1 and 2 and based on 4 and 3. So as I have seen that most of the variability is explained by first and second principal component, and after that it goes a bit down. So this will be a better representation of all my if I want to explain my data rather than this graph. Okay. So any questions still here? So this is a good question actually. Even I was asked it in an interview that suppose you have lot many number of variables and you want to choose only the significant ones. So how you will do that? So I said that I will make a principal component analysis, but the interview said that no. Principal component analysis is all for collecting the information of large data set into single one, but it will not sort out that which uh, column or which variable will have the maximum information or most vital and the most required information. Principal component doesn't do that. For that, AIC or aggregate information criteria is a good judgment to make, or is a better parameter, I would say. Why? Because it, as you know, that in the forward selection and in backward selection, AIC does a good job of only keeping the variables that make sense in building the model and ignore rest of them. But in principal component analysis, that is not done. What happens here is it is just a information collection of all the variables. It doesn't judge that which variable has a good impact or which variable doesn't have an impact. See, so you are saying that in the data set that we have, so maximum information or the maximum variability that will define my y variable, it is not in the first variable. So that is not a problem at all, because that order is not an issue. Principal component, what it does is it takes only the information and keeps its component in the order of the information that is stored. So if you're asking in regards to PCA, then first PCA will always have the largest information, irrespective of what order you have in your raw data set. So if you remember this example, we have done this in our previous class as well. This was on unemployment of different states of USA. So we will load this again and I'll try to explore that. So here I have raw data set. So now let us, so here only problem that I have is all my states are in the column, and this observations are the unemployment rate of that month. So first month is this, second month unemployment rate is 6.3, third month it is 6.1, and so on. So in this way my data set has been designed. Okay, so no, see, here there is an issue. So as I said, PCA1 will contain information of all of them. So if you're saying that temperature explain the has the maximum explanation for my y variable, so even if it is so, my principal component one might happen. What might happen is it that my PCA1 is dominated by temperature, but it will not contain only temperature. So suppose if you're saying that I have a data set, and out of that data set I have few variables in which distance and temperature uh, are two variables, and temperature shows some amount of good relation with my y variable. Uh, so what does PCA will do? So PCA, what it will do is so it might contain most of the information of temperature, but not it will not contain information only about temperature. It will contain information of all the variables. Only thing what is probable that if you're saying that temperature shows the maximum variability with y, then most of the information of PCA1 will be dominated by temperature and less by rest of the variables. So always remember, if I have any PCA, this PCA contains information of all my variables. Uh, to some extent, first variable might dominate, or my second variable might dominate. This depends. But my PCA or my principal component will contain information of all the variables that I have to some extent or the other. So after making the transpose, so I have all my state names in the row name as well. So these are my row names, not a column. And for all the row corresponding to AL, I have mentioned my employment rate. So for the first month, this was my employment rate, and so on. So this goes on in a row after making the transpose. So let us now make a PCA of this and try to understand. So here I'm not making a scale. The reason is all of them are under the same scale, and this is employment rate. So naturally all of them must be in the same scale. So for that reason, I'm not giving equal weightage to all of them. So here also I have the same thing. Of all my 50 states, variance of the first component is highest, or first three components are the major thing that I should be looking for. After that, I don't need any more apart from this. And as you see, after the fourth uh, component, it is very insignificant compared to what I had in component 1, 2, 3, and even 4. So till first three is what I should be considering to make an analysis or to understand or make any visualization that I have. So these are all my average unemployment rate for a particular month, and this is my uh, rotation factor. So that we saw just in our foods data set, that there is a rotation factor for all of the columns that we have. So for all the 500 columns here, I have all my rotation factor. Okay, and here if you can see that in the rotation factor for first component, my this one has the maximum number of variability, or it shows the maximum information that is there in the first component. So this index or this particular column has the maximum information, then this and so on, and it goes down. So this is a kind of representation that which column has the maximum information in that component. So if I, let's say, change it to 50, so so after checking after that won't be a good idea. So here, so now if I see my maximum number of information is gathered from first column, and then it goes down. Now if I go to my third, so here somewhere around 100th one as well, it is showing me the maximum amount of information that is gathered. So here I have all the numbers for all the 500. Uh, so let us see what is the value. So these are again the principal component values that I have. So after my raw data has been converted into components, so these are the raw data that I have after that conversion. So if you see, no, so it is not on the basis of correlation. It is mainly on the basis of the loading or the vector that is making the impact. So here if you see, these are my values of that column, and that has been replaced by my component. So on this my first value that will contain the information of mainly all the variables that I have, or to some extent, yeah, to all the variables, which will be dominated by few of them, a particular variable, and then so on. So from that raw data chart, this is what I have obtained after the principal component transformation. So see, here what happens is I have lot many number of variables I have, and it could be possible that out of those variables, some variables have uh, will give me hmm, a higher amount of information. So let's say the example that you have provided so far. So uh, in all the in the entire data set, I have distance and temperatures, and temperature makes the maximum impact. So and it is obvious that my first principal component will give me the information that captures the maximum information of all the variables that I have. So in that case, my PCA1 is expected to cover more information on temperature because, as I said earlier, temperature shows the maximum variation here, and it is able to explain the maximum variability. So for that reason, it is quite obvious that temperature will be dominating my first PCA. 'So now here we have all the 416 components, and let us see on the basis of that if we try to make a clustering and try to visualize that after putting a PCA, then let's see how is the results. So here I have considered three number of clusters. 3 number of clusters, and I have plotted only PCA1 and PCA2, and I have plotted all the states which are under a first cluster, under second cluster, and third cluster. So as you have seen in the previous graphs as well, so first component was actually carrying the maximum information, and second component. So here two components were good enough to show the entire explanation. And here if I consider, see, the clustering or the shape, or I could say the distinction between the two clusters that I have got here is quite smooth. So there is no overlap between one cluster and the other. Unlike what we had in the previous session that we did, when I have explained it on the basis of only two variables and not made a principal component. In that case, the result what I have got, and here the result that I have got are here it is much better compared to what was there without making a PCA. So hope it makes sense, and I'm able to convey what it actually does and how it is